AP Chem students, if you watched a little bit of videos earlier, we covered a little bit on difference between ionic and covalent bonding. This is just going to be on drawing some stuff. So this is like bottom page 5 of your notes, I believe. Okay. These are called Lewis structures, okay? Or structural formulas, but Lewis structures, the dots and the bonds. So here's kind of things. We got to be able to draw the compound. I want to know electron geometry and molecular geometry. I want to know if the bond itself is ionic, polar, or nonpolar, and if the molecule is polar or nonpolar. Hybridization, sigma pi bonds we'll do later. Okay, we'll get into that later. So I'll typically mention all these other things as we do things. These four were ionic. Did those in a different video. So that means the bond is ionic, the molecule is ionic. It's a metal. With a non-metal, there's no sharing of electrons. So let's just do some covalent molecules, which would be called molecular compounds. The covalent ones would be called molecular compounds. I can get this a little closer. There we go. So when we're drawing these, first thing I always do is I count up the number of valence electrons. So if we were doing hydrogen, it's got one valence electron per hydrogen, so 2 total. That's all I can have in my diagram. Well, there's 2 electrons in the bond. I put 2 in there. That's all I'm going to do. Molecular geometry and electron geometry, both linear. It's a non-polar bond. In other words, electrons are being pulled evenly both ways, and the molecule itself is non-polar. There's not a positive and negative end. So non-polar bond and molecule, which all of these would be that way. Non-polar, linear, non-polar bond and molecule. If we count up oxygen, oxygen has got 6 valence electrons. So we're always worried about how many valence electrons they have. There's 2 of them, so we got to use 12 electrons. Between dots and bonds, or unshared pairs and shared pairs, you need to use 12 electrons. So if I went like this, don't do this, it'll be wrong, and said, okay, give that 8 electrons around it, 2 in the bond, 2, 4, 6, 8 around it, and give that 8. Well, that's now 2, 4, 6, 8, 10, 12, 14 electrons I have used. I can't use 14 electrons, I can only use 12 for oxygen. So I got to erase, and put a double bond in. So we have unshared pair, unshared pair, shared pair, shared pair, unshared pair, unshared pair. So we should have used 12 electrons. Okay. Shape is still linear, still equal distribution of charge on each side. Nonpolar molecule, nonpolar bond. By the way, double bonds are shorter and stronger than single bonds. They have a higher bond energy. It takes more energy to make these bonds break than it does those. Shorter and stronger. Nitrogen has 5 valence electrons. There's 2 of them, so that would be 10. So if we go like this, well, that's too many electrons. That's 2, 4, 6, 8, 10, 12, 14 again. And we can only use 10. So anytime I add a bond, I erase. Again, my goal is to always get 8 electrons around nonmetals. Get 8 electrons around nonmetals. 2, 4, 6, 8, 2, 4, 6, 8. But that is still 12 electrons. So add a triple bond, erase. Unshared pair. There's 6 electrons being shared in the middle of nitrogen. Again, triple bonds are shorter and stronger, have higher bond energy than double bonds. All right. Let's go to a little different molecules. Let's say we're doing H2O. Mine's not spaced out very well. I apologize, but we'll say I'll do it above it. So I always count up the valence electrons first. Okay, make sure everything right of this stair step has 8 electrons around it. Well, oxygen's got 6 valence. 2 hydrogens would be 2, so we have 8 electrons to use, 8 total. Central element, oxygen, hydrogen. Anything right of the stair step, I give 8 electrons to. Well, oxygen's right of the stair step, so it needs to have more electrons. So it's got shared pair, unshared pair. There's 8 electrons in this molecule. 4 electron pairs around the central element. 4 electron pairs. So the electron geometry, I'm going to label as EG. The electron geometry would be tetrahedral. There's 4 unshared pairs around the central element. the molecular geometry would be bent. So if I drew water correctly, it would actually look like that. So molecular geometry, Mg, bent. The bonds themselves are polar. Electrons are being pulled towards oxygen, the higher electronegativity element. So the bonds are polar, and oxygen has a negative end and a positive end, so the molecule is polar. So bonds are polar, molecule is polar. All right, erase that. Let's say we have NH3. Nitrogen's got 5 valence plus 3. So we're going to go nitrogen with a hydrogen. Remember, hydrogens will always only form one bond. Hydrogens always only form one bond. They have no unshared pairs around them. 2, 4, 6 are being used. We have 8 to use. Nitrogen should have an unshared pair on it. Okay, which is going to force these bonds down. Okay, there's going to be some repulsion. It's going to force them down. So our shape's going to actually end up looking like, I can't see those very well, but again, there's 4 electron pairs around the central element. So our electron geometry is tetrahedral. Sorry, that's probably hard to see. Tetrahedral. And the molecular geometry is called trigonal because there's 3 things around it. Trigonal pyramid or pyramidal. Trigonal pyramidal. The bonds themselves. Nitrogen has a higher electronegativity, so electrons are being pulled towards nitrogen. So the bonds are polar, and there would be a negative end and a positive end. There's a lot more electrons up top than there are on the bottom, so it'd be a very polar molecule as well. All right. CH4. Carbon's got 4 valence, 4 there. We have 8 electrons to use. Okay, 8 electrons we can use here. 8 valence we can use. Carbon's your central element. We go hydrogen, 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 hydrogen. We've used our 8 electrons. Carbon will always form 4 bonds. Very, very rarely would. Almost always forms 4 bonds. Tetrahedral is the electron geometry, and tetrahedral is the molecular geometry. Remember, whenever there's no unshared pairs in the central element, the electron geometry and molecular geometry match up. Carbon has the higher electronegativity, so electrons are being pulled towards carbon, towards carbon, towards carbon, towards carbon. So the bonds are polar. Bonds are polar. Electrons not being shared equally. But the molecule itself is nonpolar. There is not a positive and a negative end. It's an equal distribution around there. There's not a positive and negative end around carbon, so it is a nonpolar molecule. All right, C2H4, let's try and draw. Hydroxide, I'm going to skip. I'm going to start drawing some harder ones here. We'll draw these. Maybe a couple others here. First thing, always add up your valence electrons. Add up your valence. So nitrogen's got 5 valence, hydrogen with 2, oxygen with 6, and that hydrogen with 1. So we got 14 electrons we can use. We can't use any more or less than that. 14 electrons we can use there. Our central element is typically the most electronegative element. Okay, central element is typically the most electronegative element as you're doing these things. This one's a little bit weird. Actually, I would have to tell you on this one. I would never give you one without telling you this, but this is going to have a nitrogen. Notice it has OH on it. So really what's happening is hydrogen's coming off, oxygen's coming off, and then that hydrogen's coming off there. Otherwise, you would have everything off the nitrogen, so that's why it's written like that. So we've used 2, 4, 6, 8 electrons. We have 6 more we can use. So 1, 2, 3, 4, 5, 6. That gives nitrogen 8 around it, gives oxygen 8 around it, and hydrogens are good. Okay, now I could ask you the shape around the nitrogen. Okay, the shape around the nitrogen, the electron geometry would be tetrahedral around nitrogen because there's 4 electron pairs. The molecular geometry around nitrogen would be trigonal pyramidal. You have 3 groups coming off the nitrogen and an unshared pair. Probably a pretty polar molecule, probably a little bit more negative towards this end. If I drew it correctly, this hydrogen would be a little bit more down here. This would be down there. Okay, not the best of molecules for me to have you draw at this point in time, but as we move on. This is an ion. Okay, so chlorine has 7 valence. Oxygen has 6 times 3 would be 18 electrons. It's got a -1 charge. That means we add in 1 more electron. So we have 26 electrons we can use. Actually, 26 electrons we have to use between bonds and dots. So chlorines are central. Let's go oxygen, oxygen, oxygen. Give everything 8 electrons around it. Make sure everything right at the step has 8 around it. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Chlorine had 6, so I gave it an unshared pair. If that's 26 electrons, we're golden. We're good. If it's not 26, we got to make some changes. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. All right? No, that's 26, isn't it? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Sorry. Okay, that is 26 electrons. Okay. So I drew these bonds equal distance apart, but that unshared pair is going to push those down. It's going to push those down. So that's going to change our shape a little bit. So let me redraw this the way it should be. Unshared pair up there is going to push, it's going to push our oxygens down, kind of like that. So, but in terms of bond polarity, chlorine's got a higher electronegativity than oxygen. Electrons are being pulled that direction. This probably has a small polarity as a molecule. It's probably a little bit more negative up here than there, but not very polar. So there's different degrees of polarity. It's probably not a real polar molecule, but probably a tad bit polar. Shape, electron geometry, 4 pairs. So electron geometry would be tetrahedral. And the molecular geometry would be trigonal pyramid. Trigonal pyramidal. All right, let me pick out maybe 1 or 2 more to draw here. Let me think about this one for you guys. SO2 is a good one to do. Sulfur dioxide. So sulfur's got 6 valence. Oxygens also have 6. That's 12. That's 18 electrons. Okay, this one's always a little bit tough for people to do ones like this. So I'm going to put sulfur in the middle, go oxygen, oxygen. I'm going to give everything their 8 electrons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, because it's already got find them on 1, 2, 3, 4, 5, 6. So I give everything their 8. If that's 18 electrons, we're done. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We can only use 18. So if we've used too many, the way elements or molecules use less is by having more shared pairs. So we need to make a double bond. So if I make another bond right here, they're going to share a pair of electrons. That means I have to race off of sulfur and off of oxygen. Race off of sulfur and oxygen. Now if we count up, 2, 4, 6, 8, 10, 12, 14, 16, 18. There's our 18. And everything has 8 electrons around it. So that's always your goal. Use the correct number of valence electrons. Make sure everything right at the stair step. All the nonmetals have 8 electrons around them. Let's talk about the shape. Electron pair, or excuse me, electron domain, electron domain, electron domain. So it is trigonal planar in terms of 3 different domains of electrons around there. So electron geometry is trigonal planar. The molecule itself would not stay linear. This electron pair would force these bonds down. The molecular geometry would be bent. The pair geometry would be bent. All right. There's a few examples. None of those had expanded octets. We'll get into some ones with expanded octets at another time.